All right, let's talk about something that's been at the absolute core of the AI revolution. I'm talking about the engine behind everything from ChatGPT to mind-blowing image generators. For years, it's all been about a mechanism called attention. It's been the secret sauce, right? But what if? What if that foundation we've been building everything on isn't the only way? What if there's a totally different path, one that's based not on complex weighting, but on pure, elegant geometry? So this is the big, provocative question at the heart of a brand new research paper. And it's a direct challenge to that legendary 2017 paper, Attention is All You Need, which, gave us the transformer architecture that completely took over the world of AI. Today we're going to dig into this challenge and see if attention's reign as king is really as secure as we thought. Okay, so before we can talk about dethroning the king, we got to understand why it's the king in the first place. Let's talk about self-attention. It's the absolute heart of transformer models. And it's what lets them understand all the nuance and context in data, like how words in a sentence relate to each other.
So here's the basic idea. For every single word or token in a sentence, self-attention calculates a relevance score against every other token in that same sequence. What you end up with is this massive square grid of scores, an L by L matrix that maps out how everything relates to everything else. It's incredibly powerful for sure, but as we're about to find out, that power comes at a serious cost.
Yeah, despite all its incredible success, self-attention has some really fundamental weaknesses. And we're not talking about minor little bugs. These are deep architectural problems that just get worse and worse as our models get bigger and the amount of data we feed them gets longer.
And here are the two big culprits. First up, efficiency. You know that giant matrix of scores I just mentioned? Well, its size grows quadratically. That means if you double the length of your text, you don't double the work, you quadruple it. This makes trying to process really long documents or high-def videos insanely expensive. And second, there's the interpretability problem. The whole process is basically a black box. It's so complex that trying to figure out why a model made a specific choice is, as the paper calls it, mathematically non-traceable.
And don't just take my word for it. This quote from the paper says it all. The researchers argued that the very operation that makes attention so powerful, this tensor lifting that projects all these relationships into a super complex, high-dimensional space, is the exact same thing that makes these models impossible to truly understand. We've built these amazing tools that, frankly, even the people who made them can't fully explain.
So, if attention is part of the problem, what's the solution? Well, this is where things get really interesting. The paper proposes something completely different. Instead of creating a giant matrix of weights, it says, hey, let's think about this geometrically, using a wild concept called Grassmann flows.
Okay, don't let the name scare you. The core idea here is actually really beautiful. Imagine that instead of comparing two words with just a single number, you represent the relationship between them as a unique geometric object, like a 2D plane or a subspace that's floating around in a higher dimensional space. The Grassmann manifold is just the collection of all the possible planes you could have. It's a way to encode relationships with rich geometric structure instead of just a flat score.
So how does this actually work? It's basically a four-step dance. First, you reduce the complexity of the tokens. Then, you pair and encode nearby tokens as these little geometric objects. Third, you project that geometric information back into the model's main workspace. And finally, you fuse this new geometric insight with the original token. It's a flow of information that's guided by geometry, not just by brute force weights.
And this really gets to the heart of it. There is a huge philosophical split here. Self-attention is global and unstructured. It's kind of like throwing everything into a massive, high-dimensional blender and just hoping the right thing comes out. The Grassmann flow, on the other hand, is local and highly structured. It builds understanding by carefully evolving these geometric shapes, which makes the whole process much easier to track and, hopefully, to understand.
This all sounds fantastic in theory, right? But the billion-dollar question is always the same. Does it actually work? Can this new geometric approach really go toe-to-toe with the tried-and-true heavyweight champion, the transformer? Well, let's take a look at the results. Okay, so on a standard language modeling task, the results are pretty fascinating. The Grassmann model, the Grassmann LM, performs within about 10 to 15% of a transformer of a similar size. Now, it doesn't win here, but the fact that this completely new attention-free architecture is even in the same ballpark, that is a huge deal. It proves the concept is actually viable.
So, being competitive is one thing. That's awesome. But could it actually beat a transformer at its own game? For that, the researchers moved on to a task that requires a bit more than just predicting the next word.
They used a natural language inference task, which is all about logical reasoning.
And here is the punchline. When you use it as a classification head on top of a model, the Grassmann-based version outperformed the transformer head. It's not a blowout, but it is a clear, definitive win for the geometric approach.
Now look, the margin itself is tiny. It's not huge, but its significance is absolutely massive. This result proves that for a task that involves real reasoning, explicitly encoding geometric structure isn't just some quirky alternative. It can actually be better. This is the proof that attention is not the only way to get top-tier performance.
So what does this all mean for the future of AI? Well, this is way bigger than just one model getting a slightly better score on a single test. This could represent a major shift in how we even think about designing and building these incredible systems.
So, what's the big takeaway here? First, that all-to-all brute force attention thing, it's not strictly necessary to get amazing performance. Second, we now have this powerful new tool, information flowing through the evolution of geometric shapes. And the goal here isn't to kill attention, but to decenter it, to show that there are other powerful ideas out there. And maybe most importantly, this new path could lead us to models that aren't just powerful, but are also far easier for us to actually understand.
And that really leaves us with this final, tantalizing question. For years, we've made progress by just scaling up. More data, more compute, all in a system built on this idea of brute force weighting. But what if the next great leap forward in AI doesn't come from getting bigger, but from getting smarter? From building our models on a foundation of more elegant, more structured, and more understandable mathematics? What if the future of AI is geometric?